1 2 1 2 1 2 1 2 1 2. Woo! So let's see what the question. Let's read out the question again. The binary tree is said to be balanced if for each node in the tree, the difference in get height, basically in height, but that was me trying to change in value all around. If the height of its left and right subtrees is at most 1, right? It's the same thing we just spoke about. The perfect binary tree is balanced. A perfect binary tree is balanced, just as we spoke about a perfect binary tree being a tree that where the heights are the same, right? So if you have where the heights are, the difference between the heights is 0, that's still balanced, right? It says as is a complete binary tree. A balanced binary tree does not have to be perfect or complete, right? So it doesn't have to be perfect, but perfect is also allowed. Basically, we've gone into just a bit of how this makes sense, because the variation is 0, 1. You can't go to 2 and stuff like that. So basically, a perfect tree remains, applicable. So yeah, we have that image as well. We have this image as well to also illustrate this guy. And then that this is also a balanced tree. We could see that this height here is this balance, this is not greater than 2, depth is 2 here, this depth is 1. So this works. But when you look at A as a node, you have that this is 1 2 3, this is something as 1 2 3 4, difference of 1 as well. So we see that it is node oriented when we talk about balance. Now we go ahead to instantiate our value. The class BTS, so where we have binary search tree, right? And then we have our left and right, this thing we define. So we've done this in subsequent videos as well, but just as a refresher, we just hold our value and then the left 3-pointer and the right 3-pointer, and we just went ahead to instantiate some nodes here where we then created our 3, A being the left, A the right being C, and C, B the left being D, and this as well being E. So we're just holding those values to create something for our illustration as we move forward. Now, for the brute force approach now, we do 2 things. Before we check if it's balanced, we try to first create a helper function called getHeight. Now, what getHeight does basically for us is to return the height of the left subtree and the right subtree, and then help us just basically get the height of the depth of that node, right? So basically, it just checks which one is the maximum, because obviously the height of a tree, of a node, or the depth of a node is basically of a node is basically how do you say, it's like the maximum between the left and the right. So if the left is greater than the right, you take the depth of the left. If the right is greater than the left, you take the depth of the right. So that's basically how we see the tree. So that's why we call a recursive function here, where we say if the node is equal to none, that is if we get to the base of the node, right? And then number 2 is that we should return -1. Now we'll subsequently again why we return -1, and we call the recursive case. We say left get height, call the get height function again now on the left node to continue that iteration as we go through recursive stacks. Same thing on the right. Now what do? We say when we return 1 plus the max of the left and the max of the right. So basically it's like we are basically like checking 0 -1 -1. We return that to this guy over here, return the left and return the right, and then -1 we check the max between the two of them, rather the max between the left and the right, -1 -1. And basically the max between the two of them, since they are equal, it will be just remain -1. Then we add 1 to it over here, and boom, we have 0, right? So that's how we get the 0 here. Same recursion process gives us 1 and gives us 2 eventually, and that returns us the height of the tree. Now this one returns a 1, but obviously we are picking the maximum, so 2 is the depth or the height of this node right here, or the yeah. So that's basically it for the get height helper function that we are going to use